Hello, I am Mario Ruiz and I am part of the Silence University program. Today, I am very excited to present you the composable overlays. The agenda for this presentation is as follows. I will start by motivating this work. Then I'm going to give you a high-level overview of the composable overlays. With that, I'm going to introduce the first instance of a composable overlay, the composable video pipeline. Then I will move on to the software and hardware design methodologies to explain how you can use the composable overlays and how you can create your own. Then I'm going to give you a demo of the composable overlay running on the Kriya zone. And finally, I'm going to conclude. Traditional overlays, also known as hardware libraries, are a good way to get started with an FPGA. Overlays provide software programmability within a well-defined scope. PYNQ embraces overlays and have demonstrated the benefits to reduce the barriers to entry into the FPGA world. Typically, overlays are designed in Vivado API and then imported to PYNQ. The composable overlay goes one step further and enables users to compose an overlay at runtime directly from PYNQ without using any other software tool. The composable overlay introduces three new abstraction layers. Harnessing these layers, users can compose an overlay at runtime, swap functionality on the fly, all of this while using Python APIs. These features boost runtime flexibility significantly when compared to traditional overlays. Finally, the composable overlay aims at making Xilinx platform easier to use for software developers as well as hardware designers. For this, we provide software and hardware design methodologies to make overlays easy to use, easy to reuse, and easy to extend. Now, let me give you an overview of the composable overlay. In a nutshell, the composable overlay is a stack of three layers that build on top of each other to make much easier to compose new overlays at runtime. The composable layer is based on an AXI4-Stream Switch and is where we define how data flows between different functions. The dynamic layer is based upon dynamic function exchange and enables us to swap functionality on the fly. And finally, the API layer provides a set of PYNQ-based application programming interfaces to have composed the overlay at runtime. These three layers sit on top of our traditional FPGA fabric that also provides I/O, hardware and software programmability. Each of these layers brings a new dimension to the design space that can be explored to unleash the full potential of our adaptable technology. It's worth mentioning that these pieces of technologies we are using have been around for a very long time. Our value proposition lays on providing a methodology to use and to create composable overlays in a way that is easy to use, easy to reuse, and easy to extend. Let's now explore each of these three layers in more details. The composable layer is based on an AXI4-Stream Switch, which is configured to use the control register routing. Using this configuration, the AXI4-Stream Switch behaves like an interconnect matrix and allows us to configure at runtime how the S interfaces are connected to the M interfaces. In turn, this provides us with the capability to have composable data path, meaning that we can select how data flows from one function to another at runtime. This means with one design, we have multiple concurrent software programmable paths. The AXI4-Stream Switch is limited to 16 ports. However, this gives us a total of 16 factorial possible combinations. The AXI4-Stream Switch is a game changer and is the key of our runtime composability. The dynamic layer is based upon dynamic function exchange. One of the components of DFX is partial reconfiguration. DFX allows us to swap and replace functions on the fly without interrupting the rest of the overlay. One of the key of DFX in the context of composable overlay is that augments the overlay functionality by loading the right logic into the application at hand. DFX has improved over the years, but still it's an advanced flow that adds overhead to the overlay footprint. Dynamic layer is not strictly necessary to create a composable overlay, but if used, it unleashes the full potential of our FPGA fabric. As you will see in a few slides, composable overlays can get very complicated. Keeping track of what is available in the composable and dynamic layers can be very challenging and is something you don't want to do manually. That is why the application program interfaces comes very handy. The API layer is the way PYNQ users interact with the composable overlay. The API builds on top of PYNQ and extends the default hierarchy object to expose the composable overlay functionality to the users. This is what it makes the composable overlay easy to use and easy to extend. A composable overlay is a set of static and partial bitstream and their associated metadata. The API provides automatic hardware discoveries. This is given a composable overlay, the API will automatically discover how the functions are connected to the AXI4-Stream Switch, the number of DFX regions, and partial bitstream associated to those regions. The API also provides Python methods to compose overlay at runtime, such as compose, replace, tap, and insert. More about this in a few slides. Finally, you can visualize the composed pipeline using the open source graph visualization software GraphVis. This slide is a little bit busy and shows the different layers of the PYNQ framework. I only want to focus on what is new. We have enhanced the PYNQ framework to support the composable overlay, especially improving DFX support significantly. The composable overlay extends both the FPGA side with the composable overlay itself, a static bitstream, and a collection of partial bitstream. The composable overlay also extends the Python APIs by inheriting from the default hierarchy. There are two equally important reasons why we inherit from the default hierarchy. The first one is that it provides seamless integration with PYNQ. The second one will become clear in the hardware design methodology section. As part of the composable overlay, we have introduced the concept of pipeline app, which is a method that can be used as a base to create composable pipelines and provide them to the users out of the box. A little bit more about this in a few minutes. Until now, I have discussed the fundamental of the composable overlay in an abstract way. In this section, I will present the open source composable video pipeline, the first instance of a composable overlay. I won't be able to cover everything in details, but feel free to post your questions. When we designed the composable video pipeline, we had three main driving applications in mind. Corner detect, with support for both fast and Harris algorithm, different of Gaussians, and color detect. From these three applications, you can see some functions that can be reused in green and other functions that require multiple instances in red. Based on these three applications, let's now explore how can we use the composable overlay to enable them. This slide shows you an architectural overview of the composable video pipeline for the Kria KB260 Vision AI starter kit. On the top part, you can see the input video sources. We can get video stream from the processing system or the MIPI camera. And based on the three driving applications I mentioned earlier, and with the goal to make the composable video pipeline as flexible as possible, we decided to implement 6 functions statically and to use DFX regions to add functions dynamically. In the image, you can clearly see the two layers. The AXI4-Stream Switch is the composable layer, and the 4 DFX regions are the dynamic layers. Those are hardware layers. Note that I have not given any indication about which function is connected to which AXI4-Stream Switch port, and this is because the API will automatically discover those connections for you. By the same token, and with the idea to enable much more than the 3 driving applications, we decided to implement 17 unique functions from the open source by these accelerated libraries. Those are vision functions. After careful design considerations, footprint, and flexibility trade-offs, we decided for the mapping shown in these 2 tables. The following 6 functions are implemented statically: color thresholding, filter 2D, gray to RGB, LUT, RGB to gray, and RGB to HSV. We also implemented 12 dynamic functions that map to the different DFX regions as shown in the table. The dynamic functions are sparse distributed to the heterogeneous DFX regions. Note that in the dynamic layer we have a second instance of filter 2D and two instances of dilate and erode. This is to support the different of Gaussians and color detect applications respectively. For those curious hardware designers, the DFX full plan for the CreaSum device is shown in the right-hand side of the slide. As part of the composable video pipeline, we deliver one full bit stream and 11 partial bit streams. Let's now look at a specific example how we can map one application, in this particular the different of Gaussian applications, to the composable video pipeline. We need two instances of filter 2D to implement Gaussian blur. Therefore, we need to load the dynamic filter 2D into PR0. We also need the duplicate and subtract functions that are dynamically loaded to PR4 and PR join respectively. In this animation, I will show you how you can compose the different of Gaussian applications at runtime using the composable overlay. You will also see a high-level overview how things are going on under the hood on the FPGA side. Once the composable overlay is loaded onto the FPGA using the overlay method from PYNQ, we can load the dynamic functions by calling the load IP method. Then we can compose the application by calling the compose method. These steps configure the AXI4-Stream Switch, defining how the data flows between the different functions. Note that the low-level details on how the dynamic functions are loaded and how the AXI4-Stream Switch is configured are abstracted away from the end user. In this section, I describe how to use the composable overlay from a Jupyter notebook and how you can create your own composable overlay. This notebook shows the different steps to get up and running with the composable video pipeline. It's worth mentioning that any overlay with a composable hierarchy will work in the same way. You start by downloading the composable overlay onto the FPGA, as shown in cell 1, and then you grab a handler to the composable hierarchy, as shown in cell 2. This step in cell 2 will be different for other composable pipeline where you have a different hierarchy name. Then you can explore the composable overlay. And then you can do that by inspecting the CDICT, this is shown in cell 3, and the CDICT shows the different functions that are connected to the AXI4-Stream Switch and whether they are loaded or not. And in cell 4 you can see the DFX dictionary, and the DFX dictionary shows you the different DFX regions, their associated decoupler, and the reconfigurable modules. Within the reconfigurable models, you can see the partial bit stream and the functions within that partial bit stream. Then you can load dynamic functions as shown in cell 5 using the load IP method, and in cell 6 you can see how you can grab handlers to the different functions. Then you can compose your overlay as shown in cell 7 using the compose method that takes a list, and in this list you specify the objects. And finally, you can visualize the pipeline using the graph method. This will show you the graph-based visualization, and in light blue you can see the dynamic functions. A pipeline application is much more than how the functions are connected. You also have to consider input and output stream sources and fine-tuning the function to target the application on hand. As you saw in the previous slide, getting up and running with applications, it takes a few steps. The idea of the pipeline app is to provide an out-of-the-box experience to end users. For this reason, we introduced this object. And this object is used as a base to build the tree-driven applications. And this is really a way to abstract all of the low-level details from the end users and to provide canned or pre-configured applications to them. It only provides three methods. Start will download the overlay, and also will load the dynamic functions onto the DFX regions. It will also configure the functions and compose the pipeline, and finally it will start the video sources. Play allows the end users to tweak some parameters and even modify the pipeline. And we use IPython widgets for this. And finally, stop will finalize the application. In the right-hand side of the slide, you can see an example of the corner detect applications and the parameters the end users can play with, which are the algorithm itself and the thresholding values. If you are a hardware designer and are excited as I am with the composable overlay, you might wonder, how can I create my own composable overlay? Well, I try to summarize that in these 6 steps. And step 1, you create a Vivado project, and within it, you create an API block design. And step 2, which is really important, is to create a hierarchy within the API. And then step 3 is within such hierarchy, you add the AXI4-Stream Switch and then configure it with the number of ports you want to use. Step 4, you add the pipeline control, and this is an AXI GPIO IP, which is in charge of soft reset and the FX control. Step 5, you add the static functions and wire them up to the AXI4-Stream Switch. Step 6 is just you add your DFX regions and wire them up to the AXI4-Stream Switch. And finally, you add the reconfigurable modules within the DFX regions. As a reminder, the Composable Overlay API builds on top of the default hierarchy. This means that you can create multiple concurrent composable pipelines by just repeating the process from step 2. And this is the second reason why we inherit from default hierarchy. As you can see, this gave us very good scalability in terms of composable pipeline. And finally, this is the part that everyone has been waiting since I started presenting. And now we can see how a composable video pipeline in action in this demonstration. In this demonstration, I'm going to show you the composable video pipeline running on the CreaSome. Let's start with the setup. We have the CreaSome here up and running with a PYNQ SD card image. The CreaSome is connected to the internet through the Ethernet cable. We have the USB camera connected to the USB port. And finally, we have the HDMI recorder connected to the HDMI port, which is also connected to the lab. I am running this demonstration on the Jupyter Lab environment. The Jupyter Lab is running on the processing system of our CreaSome, and we access to it using a web browser. Let's start by looking at the xmutil command, as particularly the board ID. And we can see here information about the carrier card, such as the manufacturer and the product ID. We can also see information about the CreaSome itself, such as the manufacturer and the product ID. Now let's move on to the composable part. And in this notebook, I want to show you how the different dictionaries are updated and how you can understand them when you are actually working on the composable overlay. Let's start by loading the composable overlay onto the CreaSome. Once that's done, we can inspect the IPDIC, which is a standard Python dictionary that shows the different IPs that are memory mapped into our design. You can see clearly there are 36 IP that are memory mapped here, and you can see all of them in this list. We can also observe the number of hierarchies available in our design. And for the composable overlay, we have video, composable, MIPI, and IAS hierarchy. Now let's grab a handler to the composable hierarchy and just observe the CDIC. The CDIC shows the different IP that are connected to the AXI4-Stream Switch. And if you expand this dictionary, you can see the consumer interface that is connected to and the producer interface that is connected to. On top of that, you can see that this is not in a DFX regions and it is loaded. If you look at one of them, the DFX regions, which is not loaded, you can see that it's the same information, PI, CI, that DFX that is true and is not loaded. And on top of that, you get the associated partial disk stream for this IP. You can also do more filtering on the CDIC. You can look for the unloaded IP or even loaded IP as well, and the same information is available. What if you actually want to load IPs into your design? Just call the load IP method and just pass a list with either the object itself or the name within the header. Let's do that. And now we can actually reinspect the IPDIC and clearly see that there are 40 keys, which means that there are 4 new IP has been added to this dictionary or to our design. And we can clearly see that at the very end of this list, this dictionary, PR0, filter 2D, erode, dilate, and RGB2X, XYZ had been actually added. You can reinspect the composable DIC. You can clearly see here that the PR0, PR1 has been actually populated with a partial disk stream. What if you actually want to try to work with an unloaded IP? Well, let's see. If you try to access an unloaded IP, you will get this type, which is unloaded IP. And if you try to do something with it, you will get an error. Let's now load out that function to our design and just double check that now after it has been loaded, the proper driver has been assigned to. Again, so you can double check the CDIC and see that in the PR0, the road has been added. Again, so you can double check now if we compare this with the previous one in here, you can see that before in the PR0, we had filtered to this. So when you reload some function, the previous one gets removed and you insert a new one. Again, we can see this in the IPDIC that this PR0 has been populated with a row. And finally, we can look at the DFX dictionary that shows the different DFX regions within a composable hierarchy. And the information available here is the decoupler that actually controls that DFX regions and the reconfigurable modules available for this. In this case, we have these two parts of the stream, and each of them this one has PR, erode, and dilate associated in here. And you can also see the interfaces for this IP. Now let's move on to start playing a little bit with the overlay itself. So let's just download the overlay again onto our creosome. And now let me bring up the recorder, the output of the HTML recording to the web. You can see the prompt blinking, and this is the output from the processing system to the display port or HDMI on the creosome. Now, when I will run this cell, the webcam will get configured, and the stream from the webcam will be populated to the HDMI out. And you can see hear me now. Hi there. And now we can start composing pipelines. Let's start by something simple, and let's just grab handlers to the LUT and RGB to gray functions in our design. And let's configure the LUT with a negative kernel. And if I run this, the cell will actually run this and will configure the composable pipeline on our creosome and will insert the LUT in the pipeline itself. And you can see here the output of the graph is what we actually have composed in there. And now we can use the replace method just to replace the LUT with the RGB to gray. And now you can clearly see the output has actually changed to RGB to gray. Now let's go for something a little bit more complicated, which is a different Gaussian application. Let's start by loading the necessary dynamic IP. And once that's done, we can grab the handlers to those IP and configure the filter 2D to implement Gaussian blur with a certain segment. Once that's done, we can compose our pipeline. The output, you can see the output on the stream is a little bit weak. So we will add a LUT at the end of the pipeline just to make it a little bit clear. But when we do this, we get some very, very bright. This is because the LUT is configured to implement a negative kernel. Let's just configure it to do a thresholding for every intensity above 10. We'll get assigned that to 55. And you can see here clearly that the output is a little bit better. Now, if you are not sure of what's going on under the hood, we can do some low-level inspections. To do that, we can actually enable this graph debug to true, and we will replace the filter 2D with RGB to gray just to get the graph populated again. And let's do that. And you can see that the output has changed. And also you can see that now the graph shows you how things are actually being connected under the switch. So you can see clear the consumer interface and producer interface that each of these IP are actually connected to. And finally, you can also look at how the AXI switch is configured, the array of the configuration of this. And this array provides you the information how the AXI switch is configured under the hood. This big number here means that the port is disconnected. And finally, we can stop this stream. So let's move on to the pipeline app. In the previous notebook, I demonstrated how you can create the application manually, but as you can see, there's a lot of work to be done, and perhaps it's not the best way for people to get started with this. So we introduced this concept of pipeline apps, where you can actually configure or provide pre-canned applications to people where they can actually just, with a few steps, get up and running. In this case, I'm going to run the color detect, and now I'm going to be using a file instead of the webcam. So let's start with this, run this. This will actually download the composable overlay into the FPGA, get the handlers, configure the functions, and when we start this, you can see the output of this, and the video start reproducing. And you can also see that you get an impression of what has actually been composed. As you can see, this is very complicated. This part on top here is the mask, and it's detecting yellow, red, and green colors. And this part is actually applying the mask. And we can start just playing with the application just by running this play. And this is the IPython widgets where you can actually interact with this. So in this case, we are actually running with color space, HSV, and we have noise reduction. The noise reduction is this part in here, which we can actually remove if we decide so. You can see that some changes on the stream, so we can do that. And we can also change the thresholding for this. Let me change that. You can see there how things are actually changing. In there you can see how things changing. And also you can remove the color space. We can go to RGB directly. You can see clearly how the output stream changes. We can observe the graph again, so you can clearly see here that this IP has actually been removed from the pipeline. And if we again remove the noise reduction and rerun the graph, you can see clearly that now it's a much simpler IP pipeline. And with that, I like to conclude the demonstration. I hope you have enjoyed. To sum up, I want to highlight 3 aspects of the composable overlay. Software users with little knowledge about FPGA can compose overlay at runtime. This kind of flexibility is unprecedented. The composable overlay is easy to use, easy to reuse. Also, hardware designers can add the reconfigurable models from Vivado. In a future release, we expect to streamline this process by harnessing the abstract child concept, thus making it easy to extend. As you saw from the demo, it's also really easy to compose a pipeline. The composable overlay thrives in streaming applications such as RF, DSP, and audio processing. This project is open source, and we hope the community gets interested. If you are interested and would like to contribute to collaborate, please reach out to us. Thank you for your attention.